the ocean. It's got this incredible duality, right? On one hand, it can create some of the most breathtaking light shows on Earth. But on the other, it can unleash some of the most dangerous, toxic events in the entire marine world. And the craziest part? Both of these faces, they often come from the exact same source. I mean, really, truly glow. It's this almost magical experience where just crashing a wave or even moving your hand through the water unleashes this burst of brilliant neon blue light. If you've ever seen that, you've witnessed a phenomenon called bioluminescence. But what's actually making it happen? Well, the secret is this little guy, the dinoflagellate. They're microscopic single-celled organisms just floating around near the ocean surface. And while most of them are just part of the food web, a special few have this incredible ability to produce their own light. They're like the living sparks that set the sea ablaze. So why do they glow? It's not for our entertainment, that's for sure. Scientists at the LATS laboratory at Scripps think it's a super clever defense mechanism they call the burglar alarm effect. See, when a predator tries to eat a dinoflagellate, the cell flashes. This sudden burst of light can startle the predator, making it flee. Or, and this is even more brilliant, it can attract a bigger predator that then eats the creature that was trying to eat it. It's basically a tiny, luminous cry for help. And this cry for help is unbelievably fast. The time from the initial disturbance to the flash of light is less than 20 milliseconds. That makes it one of the most rapid cellular processes known to science. It's a near instantaneous flash of biological light. A single flash is a tiny marvel, but these organisms can multiply into massive populations, or blooms. We're talking billions, maybe even trillions of them all concentrated in one area. And when that happens, the beautiful spectacle of bioluminescence can transform into something much, much more sinister. Yeah, these massive blooms are often called red tides. That's because the sheer number of organisms can actually discolor the water, turning it a rusty red or brown during the day. At night, they might still glow, but during the day, they signal a potential danger. The scientific term is a harmful algal bloom, or HAB, and for very good reason. So here's that contrast, plain and simple. On one hand, you have this dazzling, harmless light show, a true natural wonder that serves an important ecological purpose. But on the other hand, the exact same organisms, when they're in these massive numbers, can produce powerful toxins that create a harmful algal bloom. This threatens marine life, local fisheries, and even our own health. It's two faces of the very same coin. And this brings us to a very real danger. One of the big threats is called diathric shellfish poisoning. So filter feeders like clams and mussels, they consume the toxic dinoflagellates, and those toxins just accumulate in their tissues. If humans then eat that contaminated shellfish, it can cause severe gastrointestinal illness. These events can shut down entire shellfish industries, causing huge economic losses and posing a serious public health risk. And here's the core of the problem. As scientists at Scripps point out, these events are notoriously unpredictable. They seem to appear out of nowhere and can disappear just as quickly, lasting anywhere from a week to over a month. This unpredictability makes it incredibly difficult for health officials and aquaculture industries to prepare for them. So why is forecasting so tough? Well, for one, these dinoflagellates are incredibly resilient. They can survive in a huge range of conditions, what scientists call a wide ecological niche. For a bloom to happen, you need this very complex cocktail of factors: water temperature, salinity, nutrients, currents, you name it. And to make matters worse, changing ocean conditions are causing new anomalies, which means historical patterns are becoming less and less reliable. So if traditional models struggle with all this complexity, where do we turn? Well, the answer might just lie in artificial intelligence. A groundbreaking new approach is using machine learning to see the patterns that we can't, and to predict these toxic tides before they even happen. This brings us to the coast of Galicia in northwestern Spain. This area has recurrent problems with harmful blooms that threaten its vital shellfish industry. Researchers here have developed a machine learning workflow to try and solve this exact problem, using this region as their real-world laboratory. So what clues does this AI detective use? It's fed a massive amount of data. Physical variables, like water temperature and salinity from sophisticated ocean models. Biological data, like chlorophyll levels from satellites, which indicate how much plankton is in the water. And data on winds and currents, known as the upwelling index, which tells us if deep, nutrient-rich water is being pushed to the surface. The process works kind of like this. Scientists gather all that data, the physical, the biological, the upwelling info. They then use it to train several different machine learning models, essentially having them compete to see which one is the best at predicting the concentration of these toxic dinoflagellates. The winning model is then used to generate a forecast. And after the competition, there was a clear winner. In a showdown predicting blooms 3 days in advance, a model called SVR scored a 0.53. The popular random forest model did better at 0.67, but a new model called DOME outperformed them all with an accuracy score of 0.77. So what is DOME? Well, it stands out because it doesn't just look for patterns. It's a type of AI called symbolic regression that actually creates a mathematical equation to describe the relationships it finds in the data. It's not just a black box giving an answer, it's building a formula from scratch. And this is the actual equation the DOME model produced. I know it looks complex, but its transparency is its greatest strength. It shows its work, telling scientists exactly which factors are most important for its prediction. In this case, things like the current concentration of dinoflagellates and the velocity of sea currents from a day ago. This builds trust and actually improves our scientific understanding. This leap in technology signifies a major shift. We're moving away from simply reacting to the mystery of these blooms and toward a future where we can proactively manage their impacts through forewarning. And that 3-day warning is critical. The research highlights that this is enough to provide support over weekends and holidays, periods when manual water sampling often doesn't happen. It closes a really dangerous gap in our monitoring systems. You can just imagine this system in action. Real-time data from satellites and ocean models are gathered continuously. This data gets fed into the trained DOME model, which generates a forecast for the next 3 days. If the risk is high, an alert goes out to shellfish farmers and public health officials, allowing them to take preventative measures, like halting harvests. The takeaway here is that we're gaining the ability to anticipate the ocean's darker moods. This isn't about controlling nature, but about better understanding it so we can protect both our industries and the delicate balance of our marine ecosystems. Which leaves us with a final thought. We started with the wonder of a glowing sea. We now have technology that can help us predict its dangers. As our oceans continue to change, the real question is, can we use these powerful new tools not just to avoid harm, but to become better stewards of the incredible wonders our planet holds?